Okay, here we go. I left you where now we are getting into electrical signaling, and the first part of this lecture was really just building up to get you comfortable with the physics of what electricity is. So I'll review that. Electricity was just moving charges, moving charged particles. And we learned that molecules and all sorts of molecules have charges, atoms have charges. So again, just in reviewing, atoms are made up of, they have a nucleus with charged particles. So here I have positive charges in this nucleus. That atoms have a nucleus where they throw all their positive charges. The negative charges are flying around on the outside. In a neutral atom, if the negatives equal the positives, it's balanced. But if there's an excess of negatives, you've got a negative charge. And if there's an excess of positives, you've got a positive charge. So like this would be a carbon atom, and it's neutral because there's 6 electrons and 6 protons in the nucleus. But again, charged particles are easy for chemistry and for biological systems because they just use chemistry, and chemistry is built up in the machines. The parts and pieces of atoms and therefore of molecules are made up of charged particles. So that's an easy trick. And I gave you the example and even told you, just getting back to that punchline, that the electrical current coming down this axon is pretty much a sodium current. And remember, sodiums have a positive charge. So sodiums are moving down this wire, and that is an electrical signal of at least we've answered a little bit. We know, like, all right, sodium ions, and which are abundant in your blood and in all your cells because we eat a lot of salt. There's a lot of salt in our body, and our body is all in a essentially in a liquid state. That salt is dissolved. So, and again, just to take the mystery out, your table salt is sodium chloride. And actually, I told you that when these come apart, I was telling you about how ions are formed. Ions are charged atoms. Ions are charged atoms. So I told you that when this thing is dissolved in water, like I simplified and said that the chloride, when it splits apart, it steals an electron from sodium to become a Cl minus, and that leaves the sodium with a net positive charge. That's not actually true. And again, I'm not really caring so much about crazy nitty-gritty detail, although it still gnaws at me. That's why I'm sort of correcting that now. It gnaws at me when things are like simplified to the point where it's misleading, which so many lecturers do. But again, if I clarified everything crazy fully, I would never get through one topic. It's hard to find that balance. But it's even, it's even more complicated though. Like when you have table salt and sodium chloride is in a solid state and they're stuck together, the chloride has already stolen. Like it's an array. Table salt is more like, you can better think of it as like an array of ions where the pluses and minuses are literally held together in the whole solid arrangement. And then when you put this whole thing in water, they're already ions. The sodium ions can now split off and swim within the water, and the chloride ions, the negative ions, can swim off and swim within the water. So I was a little misleading. I said when you put it in water, this thing pulls off and steals the electron, like at that time. But chemistry's complicated, and these little nitty-gritty details I don't think are important they're definitely not important for our big topic anyway. But sodium ions then, we eat a lot of salt, and when it's dissolved in water, the ions are like free floating, where they're not locked together in a big solid array anymore. So in your body fluids, both inside the cells and outside, you've got tons of atoms that are positively charged and negatively charged. So you've got tons of ions in your body fluids already. They're all set. If you can harness them and control them, you can start doing electrical signaling. So we're going to get into that question of the harnessing and the controlling. How do you literally harness and rein in and control a sodium ion to specifically send that down a wire? That's where the biological and the protein machinery is going to start coming into play. It's going to do all sorts of neat tricks. And remember, proteins can move, and they can move things, and they can use energy, and they can do conformational changes. They can flip states from one state to another. And so they're like little machines. They are little machines. So again, coming back to the first original lectures, that proteins, which are just big macromolecules, they do all the work and do like pretty much all the magic of your body, of your body's functionalities, of your cell's functionalities. That your cell is really just a complicated protein machine factory. And you're going to see that again when the protein machines are setting up ways to harness like these ions to basically control them, to move them through. And that's a big part of electrical signaling, which we're going to get to in this lecture. So remember, there's an electrical signal that flows down, and that leads to a chemical signal here at the synapse, where that triggers chemicals to get spilled out. So now it's not electricity anymore. It's molecules that can bind onto these receptors to introduce other intracellular cascades. But we also realize that some of these receptors, or some of these transmembrane proteins, are responsible for, you can see it here, this plus, 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 minus, minus, minus. There's something funky going on. There's an electrical signal that is also being carried through the lipid bilayer. And remember, this whole thing here is the lipid bilayer. These kind of membrane receptors are like things that thread through, and this might be the outside of the cell, and this might be the inside of the cell. So we've got the outside and the inside of the cell. So ordinarily, let's say you've got a sodium out here. It's not going to be able to get through. And I hinted already at the last lecture that if you're going to perpetuate that signal across a plasma membrane, the plasma membrane is such a great barrier. It doesn't even let little atoms through. It can't even let a little atom through if that atom has like a charged particle. It's blocked from getting through. So it's going to have to involve some like a very specific protein allowing it and controlling its entry, and that's what happens. So now we're going to get into like the first big topic. And again, always be thinking of like how this is similar to chemical signaling and receptors and transmembrane proteins that you know and love, and how it's different. And you're going to see that there's a lot of similarities in electrical and chemical signaling. So I'm going to show you two kind of receptors. And the chemical signaling receptor, it was chemical because it was able to bind a chemical, like let's say a neurotransmitter. It induced a conformational change to the inside. Remember, this is outside of the cell, and this is inside of the cell. And then this sets off a chemical cascade. A chemical cascade that led to altered states. Let's say led to an altered state of the cell. And we talked about how that can happen. It required a lot of amplification, and a little molecule that has to have a big voice inside. You needed chemical amplification. We talked about all that in those previous lectures. So chemical signaling cascade happened through receptors. Well, the same thing there's going to be a very similar thing happening here. So I am going to now tell you another kind of receptor that can bind to a neurotransmitter. So far it's the same. So neurotransmitter can bind to another. Now this would not be the same protein. It would be similar in that you may have a protein that does chemistry on the inside. You may have a receptor. I'm going to call this receptor 1, and I'm going to call this receptor 2. Receptor 1 is binding to the neurotransmitter. It has a site that can recognize that chemical, but it induces a chemical change in chemical reactions. Now I am telling you that there's other types of receptors that are going to do this arm. They are going to bind to the neurotransmitter and somehow get an electrical signal onto the other side. But how can you do that? Now, it's a separate receptor. It has a similar surface in the sense that it's another protein, but it also has a site It's no problem to engineer, if you've got a billion years of Mother Nature, to engineer two different proteins, but they have a commonality that they can stick to the same neurotransmitter. That's awesome, because then you can let the neurotransmitter do a chemical cascade, and you can let the neurotransmitter do an electrical cascade. But we have to get the electrical cascade in. So what's one way to do it? So we've got to let this electrical flow in, and we have the ability of, like, we've got sodium that can't get in on its own. So what trick can you do? Well, this is where I'm introducing receptor 2. So receptor 2 is going to be a class. The ones that tend to do electrical signaling and electrical cascades, they are often called ion channels. And this should make a lot of sense to you. A lot of these receptors are of this type that are going to lead to an electrical signal are ion channels. They literally are like gates where there's like a barrier up top, so the sodium is out here and it can't get through anything. But when this neurotransmitter binds, it like opens up the door and allows sodium to start flowing through it. And believe me, and there's tons, like, you'll have a trillion different sodium ions. Like in this synapse here, it's probably more than trillions, but you have trillions of sodium ions. They're waiting to go. They can't get through receptors that are closed to them. They can't get through these chemical proteins because there's no like channel for them to work their way through. But there's a separate class of proteins that literally can make literally a pore, like a hole, a passageway through. But you have to open up the gate. Well, what opens up the gate? It's the neurotransmitter binding. So here, neurotransmitter led to conformational changes that led to chemical cascades. In a receptor of this type, that's going to lead to an electrical cascade. Neurotransmitter binding causes conformational change, but that conformational change is just literally opening up the door to allow the passageway of sodium ions to start flowing in. So these positive charges that are on this side are literally sodium ions that are now flowing through this ion channel. So the sodium ions are in the synapse as well, along with the neurotransmitter, and a zillion other. There's like all sorts of things in this tiny little space, because molecules and atoms are small, and the space is small, but atoms and molecules are even smaller. And there's an abundance of sodium ions here. And when neurotransmitter binds and you open the door, the sodium now has a clear path into the cell. So these receptors are literally ion channels, and ion channels can exist in two states. You can open the door so that the sodium can go in, or normally when there's no neurotransmitter around, you close the door. You can close the door. So neurotransmitter is opening the door, and then when you don't have neurotransmitter, when the neurotransmitter, let's say, gets degraded or falls off or whatever, the door can shut closed, so you can have transient signals. But the opening of the door allows the sodium to fly in. The door opening is called, appropriately enough, gating, because these are like gates that you're swinging open and close. So if this neurotransmitter is, let's say, if the neurotransmitter that causes that gates this ion channel, this sodium channel, so we might call R2 a sodium channel. Okay, and we are learning that one thing that can gate sodium channels is neurotransmitters can gate ion channels. And that can lead to an electrical signal. Because we've done it. All you need to do is open the gate. If you've got sodium flying in, you have charged particles moving. You have literally, by just flipping the gate, you've completely satisfied the requirement of having a flow of moving charges that is electricity, that is an electrical current that comes into the cell. It's crazy. You're thinking of like cells as like batteries now, but they are. They simply are, and that's not hyperbole. That's not even a metaphor. They act as like batteries, where charged particles are like stored away on one side of a membrane versus another. And when you allow a passageway, like when you turn your flashlight on, you now open up a connection and allow the charged particles to start flowing through. So you get an ion current, you get an electrical signal. And so now we're expanding our repertoire. You're learning that at a synapse, neurotransmitter gets released into the synapse, and it can cause conformational changes and lead to chemical signaling. We talked all about that, but now you're also learning that it can gate ion channels and open up an electrical signaling. Now, at this point, I haven't talked about how these two things are related. I've teased you, and I've said that the electrical signal here, the sodium currents coming down here, can trigger the chemical release. I haven't talked yet about, that bit of magic. I will. That's coming in lectures. But right now, at least, you're understanding that now from a molecular level, that just like we had receptors for neurotransmitters, some are receptors that can lead to chemical cascades, and others are receptors that can lead to electrical cascades and electrical signaling. So it's really cool. Okay, so I think I might just stop with this lecture. Should I go on a little bit more? I think I might go on a little bit more. I'm early enough where I can talk more about these ion channels. Let me talk more about these ion channels. One more slide. This figure here is showing a little bit about one of the major ways we know tons about how these ion channels work. So what this is showing you is, this is a neuron. So this is, you'd see this under a light microscope. And we can pull glass, little electrodes or pipettes, and we can stick them onto these cells. And when we do that, so here's a blow up of that process. Right here is blown up here. So this is glass. This is a plasma membrane. This is plasma membrane. This is a bilayer. This is inside the cell, inside the neuron. And this is outside. But now this is inside the pipette, this is the glass. You can literally grab onto these, and you can have this pipette, this glass thing, hooked up to circuitry. You can have it, hooked up to circuitry where you've got, ohmmeters, and you've got you've got ammeters, and you can deliver voltages, and you can hook this up to electronics. So literally, we can make an interface between really sophisticated, sensitive electronics by grabbing onto a little piece of brain cell membrane that has these ion channels in it, and it's really neat. But if this was a neurotransmitter gated channel, right? So here they're showing you sodium ions flowing through, and we can record that. If we've got this hooked up to electronics, we can record that electrical current right through the pipette. It's amazing. So we learned tons about ion channels through this. Now, if we had so all we have to do to allow this sodium to flow through is to figure out what chemicals to put in this pipette. If this is gated by a neurotransmitter called glutamate, let's say, if we have glutamate inside all this water, this is all liquid inside the pipette. If we have glutamate in here, all of a sudden, if we start putting glutamate in, all of a sudden we start recording sodium currents, electrical currents. We see it on our oscilloscope, or what we don't, whatever we are nowadays on the computer. Another thing to mention is that the gating of these ion channels, if this is gated by some chemical, that there's whole classes of them. There's so many different kinds of neurotransmitters. So let's say acetylcholine, ACH, is another neurotransmitter. If this is gated by glutamate, right, and it opens, and this will open, and glutamate opens the gate, it's like the key for the gate, Acetylcholine will not. You'll have to have another ion channel to deal with to open up a gate for acetylcholine, and another for GABA, and another for, you have them for, and another for, all the different neurotransmitters that you can have that can gate ion channels. So it's not just like one ion channel that's a gate for all these different, everything is way more specific than that. And it means that different neuron types, like one neuron whose neurotransmitter is acetylcholine, can weigh in and say something, while at the same time another part of the brain is talking to this brain cell using glutamate. It's, again, just giving you the engineering ideas about how cells can build up complexity in their signaling through ion channels. So ion channels, we've talked a lot about specificity and things being specific, but ion channels are very specific. They're specific in a couple of ways. They're specific in the neurotransmitters that gate them. And of course, remember how there's other ions? You can have chloride ion, you can have potassium, you can have bicarb, you can have all sorts of ions in here. And sometimes ion channels, like depending on the specific ion channel, maybe it will let a sodium current through. I told you that in the axon, that's the main kind that is responsible for that signal leading down an axon. But some ion channels, let chloride through, so that you have negative charges flowing through. Some let potassium but not sodium through. Some are not really so selective. They'll let sodium and potassium through. So there's a zillion different kinds in your body of ion channels, and they have different ways to gate, and they have different ions that they allow through. So you can allow different kinds of currents through. So again, it's for all you smart people who are watching this, I'm trying to trying to be too ambitious. I'm trying to give you really real crazy details here. Crazy details. So that you have some understanding of the real life complexity here that we're dealing with. Complexity. While I'm also trying to keep it simple enough, so that we can keep a focus and keep a narrative going, and I hope I'm able to kind of do both of those. So we have now introduced ion channels. They are a protein machine. They are able to they change conformations, which is called gating, which sort of opens up a permeability, like a pore, a real channel. And these are real things. These are real physical channels that get opened up so that ions can start flying through. And since ions are charged, that's a current. So at this point, we've built up our repertoire of the kind of crazy magicians, of the crazy magic that proteins can do in a cell. There's all sorts, but we're really focusing on the types of proteins that are really doing signaling. And now you have a pretty decent understanding of what chemical signaling looks like and what electrical signaling looks like. Who are the players? How do they work? Obviously, there's differences, but there's more similarities than you would think. And actually, because ions and these, bicarb is even a molecule, because sometimes even molecules can come through these ion channels. It even gets fuzzy when you're asking, well, what's the difference between this electrical signal? It's really still chemistry. It's really still a chemical signal. Sodium ions it's still like a chemical signal, right? And I would have to say, yeah, it is. These sodium ions are just charged sodium atoms. So that's chemistry. So, a lot of the terminology when we talk about electrical signaling and make it seem like, well, that's not chemistry because it's different from chemical, is sort of misleading, because it's still all chemistry, but we're just getting these ions to fly through. So we call that electrical signaling, but it's still very much chemical in nature. Anyway, so now I will stop here. We've talked about ion channels. I always try to tease you with where I'm going to go in the next video. And one thing I haven't teased you with is to build up this story and narrative is every time I've showed you that when these channels open, that there's flow in a direction. But I also told you that there's sodium inside and outside a cell. And every time I'm showing you I'm acting like the sodium ions somehow, even though there's sodium ions everywhere, they always seem to know which way to go. Like this arrow is also making that assumption where they're saying sodium is flying in, but I told you that there's plenty of sodium ions inside. When you gate a sodium ion channel and it opens, why do you get any net current at all? Why don't you get sodium for every time one comes in, or it just goes right back out? Why doesn't that happen? And I asked you a similar question last time in one of these other lectures. I said, for these ion flows, for these electrical signaling, for these sodium currents, when you have sodium ions that are flowing, where's the pushing coming from? Like, they should just be flying every which direction with no like net flow because they're everywhere. And yet somehow I've kind of snuck it in that there does seem to be a directional flow. And I'm going to talk about, and again, that gets back to that original question, like, why are we getting directional flow? Who's doing the pushing here and why? Like, how is that happening? And I'll talk about that I'll leave that little teaser for now. I'll talk about that as we elaborate more about electrical signaling in the next lecture.